plus 2 days more for late days, and you can submit latest at Friday. Does it make sense? Okay. So the second thing is that I want to suggest you not to search homework answers on web, because you won't be able to find out. I never put my problems based on materials on web. So if you search the answers on web, that's kind of a waste of time. And I guarantee that all the knowledge that is necessary to solve the homework problems are covered and contained in the lecture slides. And if you have enough time, you can also watch the lecture videos. Just carefully review the slides, you will be fine to solve these problems. And if you still feel unclear or difficult, feel free to post questions or come to the office hour. So every day we have an office hour, right? And if you just search a lot on the web, that's just a waste of time. It's a lower the efficiency. Okay, so let us continue the perception. So in the last lecture, we introduced the first learning algorithm, the linear classifier, the classical perception algorithm. Right? Perception basically is kind of instinct-driven learning algorithm. It sequentially processes each training example and only update the model weights when we make a wrong prediction. If we correctly predict one training example, just skip to the next example. Right? So in the last lecture, we explained the detailed updating rule for perception and explain why it works, both in mathematical proof and geometric implementation. And then we give several theorems characterizing the behaviors of perceptions. So first, when data is linearly separable, what is behavioral perception? If the data is linearly separable, that means I can always find a line on a hyperplane to separate positive examples from all the negative examples. Right? Then what's the behavior if you run perception? You work in any kind of orders of those training examples or training sequence. Forget about it? Huh? Yeah, exactly right. So when data is linear separable, in whatever order you feed the training sequence to the perception, it always converge and give you a separating hyperplane. Although when you use different orders of the sequence, you might end up with different separating hyperplane, but it will guarantee to perfectly separate positive examples from negative examples. That's called convergence theorem, right? But what if the data is not linearly separable? We cannot find a linear classifier which perfectly predict all the training examples. Then what is the behavior of the system? Will perception converge? Then what kind of behavior is perception? Yeah, oscillate, right? It will enter into an infinite loop. So you can imagine like it just go through a set of distinct vectors forever and ever. That's the behavior when the data is not linearly separable. So then, in the case where data is linearly separable, we give a more detailed theorem characterizing perception's behaviors. It's called mystic bound theorem. So let us read this theorem again for the review, right? So basically, the mystic bound theorem assumes two conditions. First, we assume we always have the finite feature values, meaning that for any feature vector, say xi, right, the norm of xi is upper bounded by some isometric view, you can imagine that we draw a circle or draw a board which is big enough to contain all of the input examples, right? That's the meaning of the first condition. And something you need to be aware that we are talking about those feature vectors in an augmented feature space. That means all the feature vectors are augmented with constant 1. So our linear classifier is represented as inner product between a weight vector and the augmented feature vector. The bias term is folded into the weight vector. There's some details you should be aware of. This is first condition. And second condition is that we assume the data is linearly separable. There exists a unit vector u. Unit vector means the norm is 1, such that for some positive gamma, we have every training example xi, yi, the product between the label yi and the inner product between u and xi is no less than gamma. So what does the second condition mean? What does gamma mean? Yes, margin, right? So that to explain the meaning of the second condition, we introduced an important concept called margin. So when data is linearly separable and we have forms such as separating hyperplane, then the definition of the margin of this hyperplane with respect to this particular data set is the smallest distance between the data points and this separating hyperplane. So be aware the definition of the margin. When we talk about whether a hyperplane has a margin for a particular data set, this data set must be well separated by this hyperplane. That means if you use this hyperplane to make predictions, we have 100% prediction accuracy. Then we can say, okay, this separating hyperplane has a margin. Otherwise, it does not have a margin. And then, according to the definition of margin, we can say because for every training example xi, yi, we have this product less than gamma. Right? According to the definition of the distance, when u is a unit vector, the left-hand side is exactly the distance between xi, yi, between xi and the hyperplane determined by u. Right? So we previously showed the distance, how to compute the distance between an arbitrary point and a hyperplane, right? So when we assume the weight vector is simply a unit vector, so that means the weight vector, normal weight vector is 1, then you end up with this. Let's go back. So the second condition in the mystic bound theorem simply states that first, the data is linearly separable. Second, we can find out a separating hyperplane with nonlinear margin gamma. So with these two conditions in hand, what can we claim about perception? That is, perception algorithm will always converge and make at most R over gamma squared mistakes in the training sequence. So we do not put any assumptions on the training sequence. You can fit a perception algorithm with any order of the sequence, but the maximum number of mistakes the perception will make before convergence is at most this. That's what the mystic bound theory tells us. And we have shown the proof for this theorem, right? So the proof is not trivial, but it can be decomposed into 3 steps. And the first 2 steps we use induction to prove 2 inequalities, right? And then we use Cauchy-Squar's inequality to connect the 2 inequalities. So the left-hand side and right-hand side both contain the number of mistakes d. So we combine them together, we connect them together, we get the estimates of the maximum number of mistakes. So everybody should well understand this proof. So here I want to give a more intuitive explanation of the mystic bound theorem. Right? I want to visualize it to give you a hint, right? Where does this maximum number of mistakes mean, right? So suppose here our training set, right? Those are positive examples, those are negative examples. Of course, we're talking about two-dimensional space. Then to estimate an upper bound of the mistakes the perception makes, right? How can we do that? We first need to find the maximum length of the vector, right? R. How can we do that? How can we do that? We just choose the training instance which is the farthest from the origin, right? That is this point. And the length of the vector, which is distance between the origin and this point, forms the upper bound of the normal of all the input vectors. So we get R. So you can see that when we use R as a radius to draw this circle, it must include all the training instances. So actually, R represents the range of the training instances, right? Any questions? Okay. So this is the first step. And the second step, we want to estimate the bound of number of mistakes. We want to find out a separate hyperplane. We can find an arbitrary separate hyperplane. I randomly draw a line, a black line here, right? And to perfectly separate all the positive examples from negative examples. Then we just calculate the minimum distance between all the points at this hyperplane, gamma here, which is the margin. It's the margin of this separating hyperplane with respect to the whole data set. And now with R and gamma, we can estimate the maximum number of mistakes the perception algorithm will make at this R squared over gamma squared. But you should be aware that if I run a perception with this training set, the resulting hyperplane obtained by perception is not necessarily this one. It could end up with another one. So this hyperplane is just used to get the estimate of the number of mistakes. It has nothing to do with the final hypothesis obtained by some perception algorithm. Okay, any questions so far? Everyone's good? Okay. So with the perception, with the mystic bound theorem for perception, we actually can estimate the number of mistakes perception will make for learning some specific target functions. So here I give you two exercises. One exercise is that if our target function is a disjunction with n attributes, n blue attributes, and our training set consists of all possible n-dimensional blue input vectors, and how many mistakes will a perception algorithm make during the training? How do we apply this perception mystic bound to get the estimation? And second exercise is just a slight modification of the target function. Like we can change the n variable disjunction by k variable disjunction, and how you get the bound estimation. Right? So I will walk through this first exercise because it relates to our homework 3. Give you the idea. So to apply the mystic bound theorem, right, we need to get R and gamma. Right? We need to get appropriate R and gamma so we can obtain the number of mistakes we can make. So now our target function is a disjunction of n blue variables. And what is R? What is the maximum norm of the input vectors? An idea? Think it, right? Think about it. Any suggestion? Yeah. So you just think of like among all possible n-dimensional Bloom input vectors, which point is farthest from the origin, right? You just take norm of that input vector. So when all the Bloom features take 1, then you can imagine that point must be the farthest from the origin, right? That means we have 4 n1s, right? But here, because when we talk about the mystic bound theorem, we assume all the feature vectors are augmented with a constant 1. So we're doing an n-dimensional, n+1 dimensional space. So that means the augmented vector, which is farthest away from the origin, will consist of n+1 ones, right? And what is the norm of this n+1 dimensional vector with every element being 1? What is it? An idea? So you're given a vector, right? So like a 3-dimensional vector, which is 1, 1, 1. What is the norm of that vector? Yeah, square root of 3, right? What is norm? What is norm of the vector? What's the definition of the norm of the vector? Square root of the sum of squares, right? We just apply the normal definition, right? So now if you have a n+1 dimensional vector where each element in this vector is 1, right? Then the norm of this vector is simply a square root of 1 plus n, right? So you take square of each element. Each element is 1, right? You have n+1 ones. And then you add them together, you take square root. That is square root of n+1.
Sorry, why was every element 1?
Because we want to find out the point in the whole instant space which is farthest from the origin. We want to get the upper bound of the norm of all the training instances. The norm is the length of the vector. So you will find the vector which is the farthest from origin. Use that the length of that vector as the upper bound. Any questions? Okay, assume it's straightforward. But if you have any questions, just interrupt this. Just interrupt. So in the first step, we.
Why is it square root of 1 plus n instead of square root of n?
Because when we apply the mystic bound theorem, we'll assume all the feature vectors have been augmented with constant 1. Okay? Any other questions? Okay, so we finished the first step, right? And the second step, we want to find a separating hyperplane with a non-zero margin. We get a margin in gamma, and then we can apply the mystic bound theorem here and to get a bound which is R over gamma squared, right? And then how can we find a separating hyperplane? We discussed this simple case before, right? So for a Bloom function which is conjunction of n variables, we know that this Bloom function is 1 if and only if the summation of these n variables is less than 1, right? So as we mentioned before, we can move 1 from right-hand side to left-hand side to end up with an equivalent linear classifier. So this equation actually represents the separating hyperplane. So x1 plus x2 until plus xn minus 1 equals to 0, right? So the question now is, can we use this as our separating hyperplane to get gamma? Can we? Yes? Any other suggestions? Give me a guess. Uh-huh.
Well, you know you want it to be perpendicular to the planes without touching zero. Do that.
What do you mean by perpendicular?
Well, isn't the margin perpendicular to the hyperplane?
Yeah, you can say, but margin is just a distance. So when you compute the distance, of course, you need to draw a line which is perpendicular to the hyperplane. Yeah, go on. So what's your opinion?
So I would do a unit vector that was perpendicular to that. I don't know.
Oh, that's fine. That's fine. Any other ideas?
So with that one, if you plug in like the closest point, you end up getting on the hyperplane. That's the problem, right?
You get another reason.
With the problem with this same classifier is you know at least one of the points actually on your hyperplane.
Yeah, exactly. So remember, to get it done, we need to ensure our margin is non-zero. That means every point is kind of not exactly on the hyperplane. If there's a point stays rightly on the hyperplane, what is the margin? Zero, right? So now if you just apply the mystic bound, what's the upper bound you get? Infinity, right? R over infinity. R over zero is infinity. Then the bound is not meaningful. It's meaningless. Of course, I know it will make a finite number of mistakes, right? It won't make an infinite number of mistakes. So then let us check what is the margin for this equivalent linear classifier. What is the margin for this? Can you find out a data point which directly stays on this hyperplane? What's that point? All ones? Right? Yeah. So if you say I pick x1 in 1, right? And x2 to xn are all 0. Then what's the classification function value? Simply 0, right? And that means when you calculate distance, remember distance is calculated by what? The absolute value of the classification function divided by the norm of the weight vector, right? So the numerator will be simply 0. That means this point is on the hyperplane. The minimum distance between all the data points and this hyperplane is simply 0. So although from this hyperplane we can well separate all positive examples from negative examples, we know that there are quite a few positive examples are on the hyperplane, right? So we cannot use it. And what should we do? Yeah, over a little bit, right? So it looks like this separating hyperplane is too close to the positive examples. So why not we move it a little bit, right? To move it away from all positive examples, at the same time avoid touching the negative examples, right? So suppose I move this hyperplane a little bit such that it is determined by summation from x1 to xn minus 1 over 2, rather than 1. So will this hyperplane be satisfactory? Can you find any data point which directly stay on this hyperplane? Uh-huh. Yeah. Yeah. We can check, right? So there is only one negative example, that is when all x1, x2, onto xn are 0, right? So for negative examples, the classification function value is what? Just minus 1 over 2, right? Because x1, x2 to xn are 0. But for any positive example, what is the situation? What is the case? If there is only one non-zero attribute and all the other attributes are zero, then what is the classification function? Just one or two, right? But when we have more than one variables taking one, taking two, what is the classification function? So you have a multiple variables taking one. What is the classification function? It's bigger. It's at least bigger than one or two, right? Because you only have when you only have one variable taking one, then the value is one or two, right? If you have multiple, you have more than one variables taking one, the value must be bigger than one or two. Therefore, if you summarize all those cases together, you can conclude that there are no data points which are directly staying on the hyperplane. Then we can use this hyperplane to compute the margin. So what's the margin for this hyperplane? Which point is the closest to this hyperplane? Which point is the closest to this hyperplane?
Would it be either one when they're all zero or when one is one?
Yes, exactly, right? So we know that if we have multiple ones taken by those variables, we know the value, the function value must be over one or two, right? And if we have only one variable taking one, then it is one or two. If you have full zeros, it takes one or two as well. So only when the negative example, meaning all x1 to xn are zeros, or the positive examples with only one variable taking one, they are closest to the hyperplane, and they have the same distance. And then let us calculate margin. So again, we use the augmented feature space. That means we have a unit vector, and we concatenate all the weights for each of 10 variables. That's 1, 1, 1, 1, and also fold the bias term into the unit vector, right? So minus 1 or 2, because we want this unit vector to be normalized. So we divide it by the length of this vector. So we get u, right? And also our x is augmented with constant feature 1. And then this is our equivalent separating hyperplane. And then we just use the formula we mentioned before to compute the distance between the closest point and this hyperplane, which turns out 1 over 2. Remember, this is a value of the classification function, and over this normalization constant, you get the number. You can verify it after the class. And now we have gamma and we have r, and how can we get gamma? How can we get gamma? R over gamma takes square, right? So through this example, you will know, giving you any specific target function, how you will estimate number of mistakes the perception will make learning this function, right? So I hope that will be beneficial when you do your homework problems. And also, this is a way to have a deeper understanding of the mistake bound theory. So we have finished the theoretical part for perceptive algorithm. So the remaining part is the practice. So in practice, how can we implement perceptive algorithm? And we'll introduce first, when we implement the standard perception algorithm in practice, how can we implement that? How can we determine the sequence of training data? And second, we often use a variable called margin perceptron, which encourages larger margin of linear classifier, and we'll explain why. And third, when the data is not linearly separable, we know that the standard perception will enter into an infinite loop, right? So then how can we ensure our prediction to be more robust, more reliable? That leads to the so-called Volckian averaging perception. So first, to implement the standard perception algorithm in practice, this is a commonly used framework. So basically, we go through the whole training set multiple times. One passing is called one epoch. So we choose to go through the whole data set, say like big T epochs. And then within each epoch, we shuffle the data randomly, and then we use this random ordered examples to fit to the training, fit to the perception algorithm. And here, we just use our current model to predict. And if it is incorrect, we update the weight vector accordingly. This is updating rule for perception. So here, we notice that to run the standard perception, we need to determine the number of epochs. Right? So this is called hyperparameter. So similar to like a boost or bagging, where you need to train multiple times. You need to determine what is the appropriate number of epochs or runs in the data boost or bagging, right? So this is a hyperparameter you need to determine in practice. And a way to determine, you can manually train it, or a more principled framework of cross-validation, which we'll explain later. But just be aware, you need to set up such a parameter. Okay? So, any questions? Okay. So, now let us talk about the first variant of perception. It's called margin perception. So, why we invented this margin perception? Consider we have two data sets. Or we have a data set, right? And they are linearly separable. So obviously there are many separating hyperplanes. So then there is a natural question: among all those separating hyperplanes, which one would you like to choose? Which one do you think is best? Any idea?
The biggest margin.
Why?
Because the test data is likely going to follow a similar pattern. So if it's closer, the test examples are closer to the margin. If it has a smaller margin, it has a higher risk of crossing that plane.
Yeah, that sounds good. Any supplement? You guys have a
You have an outlier. With the edge of each data, each one is consistently the same distance between all of them.
that sounds reasonable as well. Any other comment? It must satisfy. It won't incur any updates. When it won't incur any update.
It's always right.
What?
It's always right.
Yeah, it is always right, meaning that the left-hand side is always no less than eta, right? What does it mean? What does it imply?
Hard margin.
Well, how does it lead to large margin?
Basically, don't stop until you reach a margin of at least data.
Yes, exactly, right? So if you converge, right? If you converge, we know that for any training example, we have its distance to the hyperplane, which is the left-hand side, right? Is no less than eta. According to the definition of margin, right? Margin is the minimum distance between the training examples and hyperplane. That means the margin is no less than eta. So actually, eta here represents the smallest level of the margin. That's why we call it margin perception. it has set up the designated level of margin. Any questions? Everyone get the point, right? How does it relate to the margin? So of course, your learning algorithm, if the learning algorithm converges, you end up with a classifier with margin at least eta, right? But what's the disadvantage of this margin perception? What's the inconvenience if you choose? Exactly, right? So if I'm too aggressive, I set a very long theta. That means we can.
Well, I was going to ask, how do you know though if it doesn't converge, you just pick the wrong data, or it's just not linearly separate?
Yeah, that's a good question. There's no answer. You have to try it with practice. It means you have to try it. Like you have to set up some eta and see whether it converges, and you can try to increase the eta a little bit until the algorithm feels converge. Then you might find proper eta. That's something you have to tune. Right? You have to tune actual practice. That's the problem. So there are some risks, right? If you choose too big eta, the eta is too big and is larger than the margin for the whole data set. It will never converge. So what's the margin for a whole data set? Anyone remember? What's the margin for data set rather than the margin for a hyperplane?
The smallest distance between 2 points in the data set?
That's the margin for a hyperplane, right? To compute the separating hyperplane, the margin for separating hyperplane, which is to compute the minimum distance between all the data points and this hyperplane, right? But now we discussed a more general concept called margin for data set. What is the margin for data set?
The max margin.
Yes, the maximum margin. You just you can imagine like for separating linear separable data set, you just enumerate all possible hyperplanes which can well separate the data. Right? And you have many margins to pick up the largest margin as the margin of the whole data set. It represents the separability of the whole data, right? But obviously, if your eta exceeds the margin for the whole data set, you will never find out a hyperplane which exceeds the margin of the whole data set, right? So it never converge. That's a risk if you choose to use margin perception.
So you just have to guess you can't know what the max margin of the data set is. You could calculate it, you might as well just use that.
Yeah, it's usually very difficult to calculate. Like if you have a very low dimensional space, there might be some effective way to calculate. But in most cases, especially in the high dimensional input vectors, you won't be able to calculate. So in practice, as just mentioned, right? You just set up eta to be small, and we'll find convergence. That means okay, the data is linear separable, and you end up with the classifier with the margin is bigger than eta, and then just increase eta a little bit and try it again and again. Okay, any questions regarding the margin perception? Okay, so we now talk about the perceptions in the case now data is linearly separable, right? But what if the data is not linearly separable? We still want to use perception. And then what kind of perception? What kind of linear classifiers we would like to find with perception? And remember, when the data is not linearly separable, if you just run perception, it will enter into a loop, right? And then among all the linear classifiers which appeared in the running, right? Which one would you like to choose?
What's in that loop?
one in the loop. Any other suggestion?
Yeah, or something.
That's obviously that's one strategy we're going to discuss, right? Any other suggestion?
Assuming you loop, some of them will have better error than others. You want to pick a better error.
Yeah, this is one choice, right? So I think we have enough choices. So not even in the loop, just like in the whole running procedure, as long as we make mistakes, we update our weight vector, we end up with a different classifier, right? And we just check which classifier has the smallest training error. I pick the one like this one. Of course, because we will never reach a classifier having 0 training error, so the classifier is always adjusting. We want to find out the classifier which has the minimum mistakes, but unfortunately, it is not doable because finding a hyperplane with minimum mistakes is going to be hard. Then how can we improve the robustness? How can we improve our prediction? An idea?
Well, could you do something like your regression? So the cost function would be then.
You want to reduce it to an optimization problem, right? Any other suggestion? No suggestion. Imagine it's not necessary to give a right answer.
Fluidity hydrogen and slide and
Yeah, averaging, right? So that's how the Voltian averaging work, right? So now that I can now find out, or it's very hard for me to find out the hyperplane with the minimum mistakes, why not just use all possible big vectors appeared in the running procedure and use everyone to give a prediction and aggregate them together. It's very like it's very similar to like boosting and backing, right? We know boosting and backing can improve the robustness. So the first version is called Voltian perception. So Voltian perception just tracks all distinct big vectors during the running procedure. And how do we do that? Right? Of course, we need to first set up the big T, the number of total epochs, right? And then we introduce an extra variables n to track different versions of big vectors. So whenever we make a mistake during the running, right, we end up with a new weight vector. And at the same time, we record the number of the predictions made by this weight vector. And of course, when we have a new weight vector, we have to increase m, right, because we have a new version of weight vector. So we set the count of its predictions by 1. If we make a correct prediction, that means we do not have a new weight vector. We just increase the number of counts by 1 for the current weight vector. So just run it many times until we finish all the T epochs. We'll end up with the set of all distinct weight vectors during the running procedure, and each weight vector is associated with the count. The count represents how many predictions the particular weight vector make during the running, right? Any questions?
when we check the if y sub I w, is that the w sub m or just what?
Yeah, WM. This is WM.
Okay, so
WM is the current W.
The first way, once we make an error on it, we just put it aside and then keep calculating samples for the next.
Yes. Yes.
So K is the number of
C or K?
K.
K. There's no K here. Okay, yeah. You mean here, right? K is the total number of distinct big vectors. I just saw that. I just track all the distinct weight vectors. So say whenever I make a mistake, I need to update the weight vector. That means we get a new version of weight vector, right? That's why I store the Wn+1. And I set the corresponding count to be 1, right? And whenever we make a prediction, that means we make the correct prediction, we add Cm to Cm is 1.
So every iteration you have a certain number of weight vectors to be created. You then run that. Oh wait.
During the running of procedure, there won't be like a some weight vector is exactly the same as the previous one, right? Because you always add something.
Yeah.
So here, what does Cm imply? What does the count imply? So the count consists of two components. You can imagine, right? So whenever I make correct prediction, I add the count by 1, right? And finally, if I make a mistake, I will be replaced by a new weight vector, right? But this number of wrong prediction is recorded at the very beginning when I create this weight vector, because I set the count I set the count to be 1 at the very beginning. That's why I said Cm represents the total number of predictions made by the weight vector Wn. So the total number of predictions consists of like only one wrong prediction, because when we have a wrong prediction, we must change the weight vector, right? And all the remaining counts are the number of correctly predicted examples. So we can say, okay, Cm is roughly the count of correct predictions. Any question at this point? This is important to understand the voltage perception. It's not actually. It's not actually. Why? You can imagine, right? During life cycle for a particular weight vector, how many predictions it will make. So suppose it makes like 10 predictions, right? I know it must have one wrong prediction. Why? Because it got changed, right? Its life cycles, it predicts like 10 training examples. We know that 9 must be correct and 1 must be wrong. That's the same. So although it's not exactly the count of correct predictions, but roughly represent the count of correct predictions. Any question at this point? I don't want you guys to confuse at this point.
So does it act like sort of a pseudo kind of weight for each weight vector then?
Yeah, exactly. Because the larger the Cm, the larger the count, the more correct predictions it makes for this particular weight vector. So you can imagine the more important this weight vector will be. Right? And then finally, when we end up with distinct weight vectors and their counts, we can use their counts to as their vote for the prediction. That's how we do the final prediction. How we aggregate all the predictions of all the distinct weights. So you can say, for the actually new example, when we do the prediction, we first use each weight vector to give the prediction. And then we give the vote for this particular prediction with the corresponding count. And finally, we just count which particular prediction has the larger vote, and then give the prediction, give the final prediction. And through this, you can imagine, like, if a particular weight vector has the largest number of correct predictions, that means its count is largest, right? So then its prediction is more important. It's the most important. But at the same time, because we consider all possible distinct weight vectors, for some weight vectors, it might have smaller number of correct predictions. Cm is small, but it can correctly predict some hard cases. Then its prediction is integrated into the final prediction as well. That's why, in general, the voltage perception can give better or more robust performance. Any questions?
Why did you mention that CM is roughly estimation, not exactly the correction?
Okay, let me repeat again. Right? So first, CM is the total number of predictions made for the weight vector, WM, right? So suppose, during the whole life cycle of a particular weight vector, so suppose it made like 10 predictions. So how many wrong predictions it made? How many correct predictions it made? So when will a life cycle for a particular weight vector end? It must make a wrong prediction. As long as it makes a wrong prediction, its life is done, right? We switch to a new weight vector. So it must make only make one wrong prediction. And as long, the only reason it can stay alive is that it keeps making correct predictions. So suppose in his whole life cycle, it makes 10 predictions, then it must make one wrong prediction, and all the remaining are correct. Does it make sense?
Yeah.
Is there anybody still confusing at this point? Okay. Yeah, that's the voltage perception, right? So obviously, voltage perception can give a more robust and more reliable prediction, but in practice, its usage is not friendly. Why? Because we have to track all the distinct wave vectors, right? So suppose you have a very large data set, like 1 million examples, you might have hundreds of thousands of distinct wave vectors, and for each wave vector, you have to maintain the count, you have to track them, so you have to waste a lot of storage. This is not very easy and convenient to use it in practice. But I still want to enrich the prediction effect of all kinds of different wave vectors. How to do that? A better way or more popular way is called enriched perception. So how does enriched perception work? In enriched perception, we never explicitly track all the distinct wave vectors. Instead, we integrate them online with an extra wave vector denoted by A here. So at the beginning, we initialize both W, the current wave vector, and average wave vector being 0. And then during the training procedure, we do all the steps almost the same as the standard perception, except that after we do the update, no matter our current wave vector make correct prediction or not, we add the current wave vector into the average wave vector. Just one extra line of code. Then we do it wrong, like many times until big T epochs are finished. We return average wave vector, and during our prediction, we just use average wave vector to do the prediction here. That's the standard prediction with the linear classifier. So now the question is how does this average wave vector connect or relates to the voltage perception? How can we express A in terms of distinct wave vectors?
So like if you, on the previous one, the weight vector in a row, right, you have a C of 3. But in this one, you've added 3 copies of W in your A vector. So you're really just doing like a weighted sum of all of the W's throughout the whole.
Yes, exactly. Yeah, exactly, right? So if your current prediction is correct, I just add the current copy of the big vector into A, right? So no matter how many correct predictions you make, you add how many copies into A. So actually, A is the weighted summation of all the distinct wave vectors. And the weights for these distinct wave vectors are just the counts in the voltage perception. Right? So essentially, A is exactly the same as this. It's the summation of each distinct wave vector multiplied with its count. And then we do the prediction with A. In other words, we can equivalently express the prediction as the take sign over the weighted prediction with each distinct wave vector and the weighted prediction is weighted by what? By the count, CI. So now I say, we never explicitly track distinct weight vectors, but we end up with using all the distinct weight vectors in the prediction. That's a very smart way. Any questions at this one?
If you have like huge amounts, as you were talking about before, which is a problem, you ever have overflow errors and things like that to worry about? And
What do you mean by overflow?
like, for the number, it gets so large that it becomes garbage.
You mean I add up too many weight vectors such that the value oversees the limit of the.
Yeah.
Well, I think it's directly speaking, it is possible, but in practice, it won't be possible because the range of the modern computers, the range for the real numbers is really large, exceeding large, much larger than the big data in practice. Although big data in practice is surprising large, but still far away from the largest number that can be represented in computers. So we won't need to worry about that. Any other questions? In understanding the connection between this average perception and voltage perception. I want to make it very clear because you are required to implement this. Everyone is fine? Okay. Yeah, so this is the simplest version of average perception. There are many variants to even improve the robustness, but it's extremely popular. So in practice, if you really want to use perception algorithm, use average perception. So here is something simple. You should be aware about the difference between the voltage perception and the average perception. The difference mainly lies in the prediction. So for the voltage perception, as we mentioned, right? So we first use every distinct weight vector to give a prediction. The prediction is 1 or minus 1. And then each predicted label is weighted by the count. And then we just look at the total count or the total volt for each particular label and choose the one with the largest volt. But for the average perception, we don't take the sign to get the label for each distinct weight vector. Instead, we just calculate the classification function value, not transforming it into 1 or minus 1. And then weighted this prediction value with the count. And finally, we take a sign outside. So there's still some difference here. So give a concrete example. Suppose we have 3 distinct weight vectors, right? So we have the classification function value for each of the W1, W2, W3 of S1, S2, and S3. And we have all the counts to be 1, right? It's a very ideal case. And if the average perception predict X to be a positive only when S1 plus S2 plus S3 is non-negative, right? But when voltage perception predict X to be more positive. Does the voltage perception care about the skews of S1, S2, and S3? Any idea? Will the voltage perception care the skews of S1, S2, and S3? No, right? Because this is a rule, right? You first transform the classification function value according to the sign function. So when voltage perception give the positive prediction over X, if and only if any 2 values from S1, S2, S3 are not active, then we're done. We give a prediction. But there is some distinction here, right? Suppose S1, S2 is very small, like 0.1, 0.1, S3 is like minus 100. For voltage perception, it doesn't care the skills of S1, S2, and 3. It still predict X to be positive. Because one 2 positive, 1 negative, right? For average prediction, we need to add up all the 3 classification function values because S1, S2 are just 0.1, and when we add up S3, which is minus 100, it is negative, right? Then the average prediction will give a negative prediction. So this is a subtle difference between the voltage perception and the average perception prediction.
In practice, is one of those seen to be better?
Intuitively, average prediction seems to be better, right? Because we are taking into account the degree. Right? What kind of degree I classify it into a positive or negative example. You cannot like ignore this kind of degree. Right? This degree actually represents your confidence to predict as positive example or negative example. That's why I suggest you to use average perception when you address practical problems. Okay? So now we have finished up the perception part. And in summary, perception is an online learning algorithm. It is very widely used and very easy to implement. And its rule is essentially a kind of additive updates. And we can explain the rationality of this updating rule, and also have nice geometry interpretation. And also we give theorems to characterize the behaviors of perception that is called mystic bound theorem. And in practice, we have several variants. And you should know why those variants, what was the motivation to invent those variants, and why we should choose them. And after all, you should be able to implement those variants and those algorithms. Okay, any questions so far? So, okay, we have 5 minutes left, so I just want to start a little bit about the next topic. So the next topic is called agnostic learning in the basic dimension. So this is a prerequisite for us to learn the next learning algorithm for the classifier called Paul vector trees. So what is agnostic learning? Agnostic learning is another branch of computational learning theory. So previously when we discussed the path learnability, we want to derive some generalization error bound, right? We assume we can always find a powerful learning algorithm which results in a consistent hypothesis, meaning that we can guarantee zero training error whenever target function, whatever target function you use. Right? Obviously, this is true. Idealistic. Some of you have mentioned that this is not very practical. We discussed it all this time. A more practical case is that actually we cannot guarantee a zero training error. In this case, can we still give some reasonable estimate about the generalization error? That's what the agnostic learning wants to address. But you will see that even for agnostic learning, the bound we get still assume the hypothesis space is finite. When your hypothesis space is infinite, the bound about the generalization error or the sample complexity is not meaningful at all. Then there comes a question, at least we know for linear classifiers, linear models, the hypothesis space is infinite, right? How can we address this problem? That will require us to invent a new measurement of the model complexity. When the hypothesis space is infinite, we still need to have a measure, a finite measure, to evaluate the complexity of the model. That is called basic dimension. And regarding the theoretical derivation of this dimension, this is not our focus, but you need to know what is this dimension and how to calculate this dimension. And I will give you results about the generalization error bound using this dimension. That can characterize the performance, the general performance of the linear classifier. And also, those bound motivates the invention of the so-called support vector machines. Okay, so we'll continue the discussion on Wednesday.